Today I'm going to talk about my recent work on building a practical zero-knowledge proof for PSPACE, and this is a joint work with Ashwin, Ning, and Kuldeep. So I want to begin my talk with a little bit of history. The first zero-knowledge proof protocol was proposed. Back to then, there's no zero-knowledge protocol for general problem, and at that time, the definition of zero-knowledge proof was still taking shape. After a while, we found that every language, if we have an interactive proof system, then we can also build a zero-knowledge proof system for that language. And in early 19, there is a breakthrough in about zero-knowledge proof, especially about how expressive zero-knowledge proof is. We show that in the literature, we show that every language in PSPACE, there is interactive proof system. Therefore, by combining with the result we had before, every language in PSPACE, there is a zero-knowledge proof system. Then recently, we see a lot of progress about designing zero-knowledge proof protocol. We see a lot of very efficient and practical zero-knowledge proof design and their application in real-world domains, such as blockchain. But most of these protocols are focused on language of NP. And until recently, my colleagues and I designed an efficient zero-knowledge protocol for core NP. And the idea of designing a zero-knowledge proof protocol for core NP actually comes from another field called automated reasoning. In fact, automated reasoning has been looking into PSPACE problems for a while, especially while the language of a quantifying the Boolean formula called QBF. In 1995, there is a proof system called Q resolution proof system that was introduced as a foundational refutation calculus for quantifying the Boolean formula. And then there are some algorithms to show how can we systematically derive the quantifying extended resolution proof for QBF. After a while, there are a lot of proof system was built on top of the extended resolution proof system, such as this proof system based on expansion and instantiation. And recently, the development of QBF is more than about solving the quantifying the Boolean formula, but also generating proof as long as we have the evaluation for QBF. If you don't know some terms in this slide, such as zero-knowledge proof or QBF, don't worry, I will explain it later. Okay, and what I want to emphasize is my work. This work is stand on the shoulder of this both fields. By combining the progress of proof system for QBF and the recent technique on the zero-knowledge proof, finally we find that is the best time of offering this efficient zero-knowledge protocol for PSPACE. Okay, that is a theoretical interest of building the practical zero-knowledge proof for PSPACE. I also want to motivate our work using some real-world problem that is called black box checking. So think about a scenario where there is a white hat hacker who wants to prove the existence of bug in a software, but he doesn't want to review it until he got paid. So this is not a contrived setting, actually. One DARPA project, and one of the goals of a DARPA project is about this. And when I was a part of this project, we find the bottleneck is all about the scalability, because the software or the system can be very large. And if you want to prove the existence of the bug using all this kind of existing cryptography tool, then the design becomes too large to be encoded entirely. And what we found is if we forgot all this confidentiality requirement and just focus about proving the existence of a bug, in the literature, there was some approach to doing that. That is called black box checking. The idea is the behavior of this bug actually can be independent of the implementation of most of the part of the software. For example, if I have A, B, C, D component of the software, in a lot of times, the behavior of the bug is only related to a component. And for BCD, we really don't care. We really don't care about how they are implemented. So that is the idea behind the black box checking. So what we do is we can encode this independent component as a black box, and then this black box checking problem will be reduced to QBF solving, and proving the existence of a software bug will reduce to QBF evaluation certification. And our work, I want to show this evaluation result at the beginning. We do benchmark our ZKP for proving QBF using the QBF generated from black box checking. And we show that for the black box for QBF generated for black box checking problem, we can verify the evaluation, that is verifying the existence of a bug within 1 hour using our protocol and this QBF for black box checking problem. Okay, this slide just want to impress you and show you how practical our protocol is. And I hope you are interested in how can we achieve that, and follow me with the rest of the talk, please.
Maybe you're going to go over that, but I have a question regarding about exactly maybe what you mean by coefficient here, because my current understanding is that from IP equal PSPACE, right, you can use PCP to do IP.
Yes.
And now if you use Killian approach where you make all clear and all that, then you can get a non-interactive proof for PSPACE, right?
Yes.
Then I guess maybe if you plug commitments, then you get zero knowledge. But
yeah, so I think I got this question a lot of time. So what does that mean by being practical? Okay, so being practical means we can really prove the evaluation of a QBF the idea is proving the evaluation of a QBF for real world problem. So of course you can do whatever the theoretical part as you just described. However, if you really come into real world QBF, QBF from real world application, you'll find that the size of a QBF is very large and the number of variable is really large. And actually, we do have some preliminary results that use some check protocol and then use these commitment schemes. We find for many of these instances for black box checking and also some other benchmark, if we use this sum check benchmark for real world application, not just the benchmark for QBF, for QBF formula, we find for many real-world applications, the sum check-based protocol doesn't scale. The main reason is not about the proving, it's about solving. So the solver needs to, if you remember the sum check protocol, the prover actually needs to give the evaluation of some intermediate polynomial to the verifier. And it takes a lot of space for the prover to find the evaluation, what the evaluation is. And that is a bottleneck. And being practical means, okay, here, the proof, as long as the prover can solve this formula, can solve this QBF formula, then the prover should be able to prove that. And theoretically, that should be true, but in fact, if you just use sum check protocol, the prover needs a lot of additional work to do this, to do the proof. So that's what I mean by being practical. Okay. Now I don't know how many of you heard about the non-proof. If you heard the non-proof, raise your hand. Okay, then I can skip this slide. Well, this is my favorite slide. We can skip that. Okay. I want to talk about how. But I want to emphasize what the setting of the non-proof. In this setting, we have a prover and we have a verifier. The prover knows an input that makes the circuit's output 1, and he wants to convince the verifier that she knows such X without reviewing any information about what X is. And the verifier tries to validate the prover's claim about her knowledge of this input. Both prover and verifier can be malicious in the sense that the prover may cheat about her knowledge of such X, and the verifier may try to learn what X is. Okay, there are a lot of ways to achieve the non-proof. One typical way is commitment proof, and so we need something called commitment. So if you don't know commitment, you can think of commitment as a ciphertext that hides the underlying value. And at the same time, it enables the verifier to check the relation between the underlying value. So in this slide, the verifier should be able to check if the product of X0 and X1 is index X2 without knowing what their real value is. And at the same time, it will prevent the prover from cheating about the underlying value. For example, if the X2 is a commitment of 0, but the prover tries to convince the verifier this commitment commits value 1, then the verifier should be able to detect that the prover is cheating. Okay, that is a commitment. Once we have a commitment, then we should be able to build the analogy proof protocol using the commit and prove paradigm. So the idea is we can have the prover commits the value over all wires over the circuit. And then we can have the verifier check if the input and output of each gate is consistent just over the ciphertext. For example, we can have the verifier check if the product of X1 and X0 is indeed X5, but only over the commitment, and so on. So the verifier will check for each gate, and at the end, the verifier check if the output is reading the commitment of 1. If the output is reading the commitment of 1, then the verifier should be confident that the prover really knows the input that makes the circuit output 1. Okay, that's a commit and prove paradigm. So the idea, the takeaway of the analogy proof part is by using the commit and prove, the verifier should be able to verify the relation between private value. And what I also want to emphasize is the verifier should be also able to verify the relation between polynomial using the same like arithmetic circuit or this kind of thing. For example, the verifier should be able to check if two confidential polynomials are equivalent, or if a private polynomial divides another private polynomial. So why this is important? That's because that's all we need for building the practical analogy proof for PSPACE, and I will explain later. And if you don't know the analogy protocol, or if you are not familiar with the literature, this slide is all you need for understanding the rest part. Okay. Now we have this tool, and most of the time when we design the analogy protocol for real-world application, the challenge becomes how can we arithmetize the problem? That is, how can we express this problem using this constraint over value or this constraint over polynomial? And the next I will explain how can we express QBF evaluation, which is a logic language, to this polynomial constraint, which is arithmetic language. Okay, so I have been talking about QBF for a while. So what is a QBF? In this work, we focus on QBF in PCNF, which is a prefix CNF. So a CNF is a Boolean formula that consists of a conjunction of disjunction of a literal. So we call this disjunction of a literal a clause. And a CNF is a conjunction of all these clauses. And we also call this variable, this variable or negation of variable or literal, okay, for the rest of the talk. This is a typical CNF, that is a conjunction of this disjunction of literal. And a QBF, or in PCNF, add one prefix before the formula. So in this example, we have the prefix. It reads as for all x0 exists y, for all x1, this formula holds or not. Okay, since as you can see, we only have a variable x0, x1, and y. So this all variables are quantified. So this formula can be either true or false. It's not satisfied or unset. This formula can be either true or false because all variables are quantified. Okay. So by introducing this quantified prefix, we actually give additional information to the variable. One is a type of the literal. So according to what quantifier annotated to the variable, we have for all literal and existential literal, for all quantifying literal and existential quantifying literal. So in this example, y is existential quantifying literal, and x0 and x1 is existential, is for all quantifying literal, x0 and their negation. Okay, so this is a type of the literal. The prefix also give an order over the neutral. Because if you think about this prefix, actually it defines some dependency over the neutral, right? For example, y should depend on the value of x0. Okay, now I want to ask you a question. So do you think this formula is true or false? How many of you think it's true? How many of you think it's false? Okay, why is false?
Like x0 is false, then whatever your choice of y is, the first two clauses you can find some x1 that makes it false.
Exactly. So actually, you can have this binary tree, right? So no matter what, you can find some x0's assignment that after that, no matter what value you assign to y, there always exists assignment of x1 that needs to false. Okay. That's why this formula is why this QBF evaluate true false. Okay, now I want to ask you another question. So if I want to prove this formula indeed evaluate true false, how can I do that? Like the simplest way.
Well, I guess just over all the existence, you could just try all the y's and then show that. Well, you give an x0 and then just say that for all y's, you give it x1 that causes it to be false.
Yeah. So what you just suggest is maybe we can just give this tree to the verifier, and then verifier can just run this tree and to check if that the claim is true, right? So, however, if you give this tree directly to the verifier, then the size of the proof should be always exponential. Okay, that is prohibitive when we come to real world application. So now next I want to show you how can I prove the evaluation of this formula by using two rules. The first rule is called for all reduction. So the idea is now if this clause, which is one of the clause, or which clause? Okay, this clause. If this clause 2 is indeed true, let's say if this clause is true, then what does that mean? That means this four paths should need, all of them should need 1, right? And if you remember, x1 is for all quantified, right? So that's the last layer of this tree. So what that mean? That means these two paths should need to true. So what that tell us? That tell us if this clause is true, then we can derive a new clause that is not x0 or y. If this is true, this should be also true. Okay, so that's how we derive new clause by using for all reduction. From C2, we derive C4 by using this for all reduction. That's one rule. And but I want to emphasize here is you cannot further remove x0, even x0 is for all quantified, because before that there is a y, and y is existential quantified. Okay, so that's why you cannot further remove x0. In general, if you have a clause that has a bunch of existential neutral and for all quantifying neutral, you can remove all for all quantifying neutral as long as their order is greater than existential neutral. Okay, so basically you can remove all neutral after the largest existential neutral. Okay, that's in general by for all reduction rule. And the order is defined by the prefix. Okay, that's for all reduction. We already got one clause. Next, I'm going to show you another rule called existential resolution. So a resolution means you can eliminate the conflicting neutral and then combine the rest to get a new clause. And for existential resolution says in QBF, we can only eliminate the neutral as long as they are only when these neutral are existential quantifying neutral. Okay, so in this case, we by applying existential resolution to clause 4 and clause 5, we got a not x0. Okay, Okay, now I'm going to show you how can I prove the evaluation of this formula using these two rules. So we already have a one for quantifying for all reduction and one existential resolution. Okay, this is in general what existential resolution means. So you can remove the existential quantified neutral and combine the rest. And there are some additional requirements that says the rest of part cannot be a tautology. Otherwise, this is not sound. The proof is not sound. Now again, I apply for all reduction to clause 6. That is what we derived before by applying clause 4 and clause 5. The reason we can apply for all reduction now is because there is no existential literal in this clause. So we can directly remove x0. Okay, and now because we remove x0, we got what? We got an empty clause. And this empty clause actually shows why this input formula QBF is false. Okay? And the way we derive this empty clause is called a Q resolution proof. And the way we derive it consists of a proof for this QBF evaluation to false. Okay? That is quantifying the resolution proof. And believe it or not, as long as a QBF this QBF is closed and is in PCNF, if this QBF is unsatisfiable or false, if and only if there is a sequence of Q resolution steps that needs to choose the empty clause. So basically that means this Q resolution proof is reputationally complete. Okay, so I want to emphasize two things for this theorem. One is this theorem actually requires all clauses in the input formula is already for all reducted. Okay, so here this is not for this input formula. The clause in the input formula is not all for all reducted, because actually you can further simplify the C2 by applying for all reduction to by applying for all reduction to C2. You can further simplify it. Okay, and another requirement or another thing I want to emphasize is what that means by a Q resolution step. We say for existential resolution and for reduction, a Q resolution step means existential resolution followed by a complete for all reduction. So if you think about the for all reduction, you can remove a subset of neutral that you can remove. Okay, but here we require that you after whatever existential resolution happens, you always follow the resolution by a for all reduction and remove as many neutral as you can. Okay, that is a Q resolution step. So as long as the formula is close to QBF and in CNF, and if the input formula is all the input clause are for all reducted, then we can always build a Q resolution proof consisting of this Q resolution step that needs to empty as long as the formula is false. Okay.
No question. For the first requirement, why do we need this? If this is not, why can't you just apply?
Oh, because we want to unify the proof. We want the proof always always consists of this one. Always consists of this Q resolution step. If you don't require the first one, you will have some separate for all reduction at the beginning. So we always want the proof always be existential resolution for all reduction, existential resolution for all reduction.
Oh, is that the definition for Q resolution?
Yeah, it is a definition for Q resolution proof. This is simplified. So yeah, okay. So so once we have this format, the reason this is also good for good when we're building the zero-knowledge protocol. So we always have one step that consists of two rule application. Otherwise, you need to hide which rule you apply.
Oh, okay.
Yeah. Okay. Now, now let's go back to our setting, on building the knowledge protocol for QBF evaluation. In this setting, we have a QBF formula. which is public, and we want to prove that the evaluation of the formula, and basically using this Q resolution proof. So in this setting, the prover wants to prove this QBF is unsatisfiable, and at the same time, he wants to keep this proof private, and the verifier wants to validate the proof's claim about the unsatisfiability of the formula. But at the same time, the verifier wants to learn information about the resolution proof or Q resolution proof. So if you still remember the commit and prove paradigm, if we have this paradigm, the idea of building this ZKP is relatively straightforward. So how can we do? First, we just commit this Q resolution proof. And then we just show over this commitment, this Q resolution proof is indeed a valid resolution proof. However, the gap is now, when we talk about Q resolution proof, this is a logic language. And what we have when we talk about commitment or this kind of thing is arithmetic language. So we need to find a way to connect them together. Okay? So in fact, we find the language that's connecting this logic and arithmetic language is the language of set. Okay, that is the language of set. So what that mean? If you think about clause in CNF, a clause is a disjunction of a set of literal, right? So, this literal are always connected by a disjunction. So we can treat this clause as a set of elements. Okay? And then what do? We encode this set using a polynomial. The root of the polynomial is the element in the set. Why we encode this set, why we encode the clause this way? The reason is as long as we encode the clause using a polynomial like this, we can always reflect the operations over the clause to constrain over the polynomial. So now I'm going to show you how can I encode the constraint imposed by the resolution using to the constraint over the polynomial. So here, this is a resolution, forgot the existential part. This is a resolution where we have clause A and we have clause B. And this clause R is obtained by applying resolution to clause A and clause B and eliminate X2 and not X2. Okay, this is the clause R. And so if we want to prove that clause R is indeed obtained by applying resolution to clause A and clause B, in the language set, what we really want to prove? We want to prove, okay, clause A is a subset of clause R union with this pivot literal if we treat this clause as a set. And clause B is a subset of clause R union with not the negation of the pivot literal. So if clause R is indeed obtained by applying resolution to clause A and clause B, then when we think about clause A, B, and R as a set, they should satisfy this constraint. Okay, that's when we think about the resolution in the language set. Then this constraint over sets can be further reduced to deviation relation between polynomial. Because you just recall the root of the polynomial is the element in the set. So if the relation between the sets holds, then their corresponding polynomial should satisfy this relation. Okay, so then we reduce verifying the logical relation to verifying their corresponding relation between their corresponding polynomial. Okay. That's how can we bridge the logic language and arithmetic language. But what I want to emphasize here is there is actually a gap. It's because if you think about the literal is either a variable or negation variable. And when we talk about polynomial, we always talk about the polynomial over some field, right? So you need some encoding from the literal to field element. So the literal encoding scheme we use for propositional Boolean formula where we don't have this quantifier prefix is the following. So we have the highest bit of this element, this f to the k element to be the sign of the neutral. So in this example, x5, the sign of the x5, this neutral is positive, so the highest bit is 1. If this is a negation of x5, then the highest bit should be 0. And the rest part of this binary string will be the binary encoding of the index or identity of the neutral. So here the index of the neutral is 5. So this is the binary encoding of 5. Okay, that's how do we encode neutral? How do we encode a neutral to a field element? And we use f to the k for our field. Okay, and that's a particular scheme we use in our protocol. But in fact, if you want to prove the resolution relation using the polynomial constraint, as long as the encoding scheme is injective and satisfy this relation, it should be fine to use. The reason we ask for this constraint is because it's just for efficiency. So you can efficiently verify if the encoding of two neutral are two neutral are conflicting or not, because they are only involve like addition arithmetic. Okay, that's okay.
So the sign here is whether or not you should apply a not, right?
The sign is what?
It's on whether or not you should apply the not gate, right?
Yes.
So where do you place the value?
This is okay. This is the encoding. Okay, why we have the sign of the neutral for the highest bit is for the highest bit. It's just to satisfy this relation.
Yeah, but then if for instance now x5 takes value 0, how do you encode that? Oh, there's no encoding about the value of the neutral, or?
You mean if I have a negation of x5?
No, the x5 takes a value.
X5 is the neutral.
You don't assign value to it?
Okay. So we are talking about a formula, right? And the formula is about a variable. Okay. So now we just reasoning about this formula. So every x5 will be treated as symbolically. So there is no assignment to x5. So this is just the encoding of this variable. There is no assignment or semantic to the x5. It's just representing the variable of x5.
Okay.
Okay.
Can we go back to the previous slide for a moment? Yeah, so like at the bottom here we have like x minus LP, but it's like negative since we're working in like a killer characteristic too, like subtracting LP is just the same thing as adding LP. So like should it really be like plus?
This should be like in f to the k, this should be plus c.
Yeah.
Yeah.
Okay.
Yeah. So I use CS there, but it shouldn't be true if we think about f to the k. Okay, because if it's f to the k, then they are the same, right? So that will violate the requirement of being injective mapping.
Yeah.
Okay. That is just for like for simplicity. Like okay. I hope you or you understand the encode.
Sorry, I'm still confused. I thought, can you go back to the previous one? I thought you were saying that these values, the values of these variables are field elements. We're talking about the representation of these variables.
The representation of this variable because we are now encode the clause. So for the clause, we don't assign value to the variable. It's just a clause. So we try to encode this clause using polynomial. So basically here, for example, the clause x1 and or x2. So we don't assign any value to x1 and x2. We just want to represent this clause using some polynomial. So basically, and then we have the element for x2, and here this is the element for this corresponding neutral.
Oh.
And this should be some encoding of the neutral, and we don't assign the value. So just to re-emphasize that when we do this resolution proof, we never assign value to some certain variable. Yeah. Okay. We just like eliminate what is symbolically.
I see. So you write. So you go from to represent all these clauses using a polynomial.
Yes.
I see.
Yeah. Okay. And yeah, and this is encoding. How can we encode a neutral? There is no assignment or value to the neutral, to a polynomial. Okay. Because if you remember when we do this Q resolution things, we never talk about the value of this variable. We just do this operation over this symbol or over this representation.
But then do you need to additionally prove that these encodings are done correctly or?
So the mapping from the neutral to the mapping from the neutral to the field is public. Yeah. So the only thing, if this is not injective, then that will make the prover's task harder. And if that doesn't satisfy, and the prover, we show that the prover cannot abuse the violation from deviation from this encoding scheme to get a sound proof, even the proof is not even the formula is satisfied. Okay, and actually there. You will see this actually is a relaxation of this constraint. Because if we just encode the relation using this, clause R can have some other neutral. For example, the clause R can have X can be X1 or X3, right? So clause R can be larger. But if you have a larger clause resolvent, that will only make the prover's task harder. Because the goal is to eliminate the neutral instead of adding the neutral. So it's fine if we relax this constraint. Okay, that's also one reason we get efficient ZKP for verifying the resolution. And at the beginning, we indeed check if the clause R is exact obtained by applying resolution. And it shows by removing this constraint, we actually improve the performance by half. So that's some relaxation in the ZKP setting. Okay. Okay. Now I just talk about the resolution, and we don't talk about. I haven't talked about how can we handle the quantifier and the order and the type of the neutral. So if we come to QPF setting, we have some additional information we need to check for neutral. So one is their type. We want to check if you remember when we're reasoning the QBF, we need to check if some certain neutral is for all neutral or is existential quantifying neutral. Another thing is we need to check the order of the neutral, because if you remember when we remove the neutral for all neutral, we need to check if their order is indeed larger than the existential quantifying neutral. So the encoding we had before is not sufficient to encode all this kind of information. So to overcome this, we instead of have the binary part, there's the rest of the binary string to encode the index of the neutral. We have it to encode the order of neutral. Okay, for example, here. Okay, you just remember like X0 has order 1, 2, 3. Okay, Y is order 2 and X1 is 3. So in this example, the rest of the part of the binary string is the order of neutral, which is 2. And the X0 has the order of 1. That's why this encodes the number 1. Okay, and by doing this, we actually can check if the order relation between different neutral, and once we commit this field element, we can also check their relation using either lookup table or some arithmetic conversion in ZKP. Okay, that's the high level idea. We can encode the order of the order information of the neutral using their field representation. Now let's come to existential resolution. Once in existential resolution, we check the resolution relation, but at the same time we need to check if the literal or the pivot literal is indeed existential quantified. So to do this, we have two different sets. One set include all quantified literal, and one set include all existential quantified literal. And besides checking the relation imposed by the resolution, we also check if this the pivot literal is indeed an element in this existential set. That's what we check here. Okay. That's for all for existential resolution. And now let's come to for all reduction. For all reduction is a little bit involved. So if you let me explain it step by step. So let's say the input clause is or premise clause is a clause. If we sort all elements according to their order, we sort this literal according to their order in the prefix, then we can find the largest existential, let's say Y is the largest existential quantified literal. For all reduction or accompanied for all reduction means we need to remove all literal appears after that. And this Y, the largest existential quantified literal along with literal in the right hand should be remains in the result clause. Okay, that is what should be removed and what should remains. Okay. And if it requires all literal on the left of the largest existential literal to be removed, then it also ensures a complete reduction that fulfill all requirements of the soundness of the Q resolution proof. Okay. Now to encode to verify if this for reduction is correctly applied, what we do is we first have this two clause set in the set language. Let me say it first in the set language. We first have two additional sets. One indicates the things. This is a typo. One indicates the things remains in the result, and one indicates the things that is removed. Okay, we have these two additional sets besides the input clause and output clause. And then we check if all elements, additionally, the prover also need to commit the largest existential literal. Then we check if every element in the removed set, the order of the literal should be greater than the largest existential literal. And we also check if every literal in the result literal, the order of this literal should be smaller than the largest existential literal, so that we know Y is indeed the largest existential literal. And at the same time, we also need to check first Y is indeed existential quantified literal. And at the same time, for every literal we removed, the literal should be for all quantified literal. Okay, that's the additional things we need to check. So reflect to the polynomial constraint, we have this one-to-one mapping from the set language to polynomial relation. So this check if the order correctness in the remaining part, in the removed part, and if and the correctness of the removed part of the for all reduction. And this checks the order correctness in the result part and the correctness of the correct construction correctness of the clause in the result part. And this is for the correctness of clause A and the correctness of clause R, as well as the type correctness of literal removed and type correctness of the largest existential quantified literal. Okay. But if this is a little bit, if I talk about this a little bit quickly, just think about all this constraint using the language of set, and then you can always encode the membership or subset relation using the polynomial. If we encode the use the polynomial's root as the encoding of the literal. Okay. Question.
Sorry, I just wonder. So for each of these, the first two lines, do we need to
Sorry.
loop through every single literal? Like, do we need to loop through every single literal that is less than y and check if?
Yeah, you need to enumerate that, and you can do that. What we do is we do that in a batching way, so to make it efficient.
Oh, so we do need that. We do need to check for every literal.
Yeah, yes. You need to check for every literal in the clause. Yeah. So because when we design this protocol, we try to find a way to avoid that, but we find if we don't check for each literal, that will actually give a chance to the prover cheating about. For example, it says, okay, if I just check for some certain literal, it can always embed some larger or some literal with larger order in the set and violate the soundness of the proof. Okay.
I see. Yeah, I'm just trying to make some check work here.
Regarding that, can that be avoided if you instead query the prover on a random subset of those literal?
If I have the prover query what?
If you check the prover on a random subset, instead of because right now you say that you will need to
For every no, because why that is no. So if you use some random subset, then that means if you select some random part, you get a high chance of let's say if you select a random subset, then even it's very small chance you got the subset that enable the prover cheat successfully, right? If you want to have some random subset, but the problem is as long as we can show that as long as there is just one literal that violates this order requirement, then the prover should be able to construct some proof that is construct some proof for a formula that is satisfied, but the prover should be able to fake some proof that. So as long as there is one literal, so that's why we need to check for everyone instead of some random subsets. Okay. Okay. So that's how can we reduce all the relation over the literal and clauses to polynomial relation, and at the end we verify all these polynomial relation in ZKP. So that's put them together, we got a relatively efficient ZKP for PSPACE problem using this QBF. Okay, and there are some other details about this work. One is how can we make sure that the clause is used for all reduction and resolution is indeed the clause that in the formula or the clause that has been derived before. We use some special variant of lookup table argument in the KP. And also by using this Q resolution proof, what the prover really prove is the evaluation of the QBF. But if you are familiar with the QBF setting, when we talk about QBF evaluation, we also talk about something called a winning strategy. So what that mean? If you think about a formula that's for example, if we have for all x exists y, some formula always true, that means y is a function of x. So no matter what x is the value you got for x, I can always, according to the value of x, I can always find a y that makes the formula true or false. So basically, this function of y over x is called a winning strategy. And using Q resolution proof, we can only prove the evaluation of a QBF, but it doesn't reflect the prover's knowledge of this kind of winning strategy. But in practice, this winning strategy is very important knowledge to show, for example, in the first motivation about proving the bugs. This winning strategy actually tells the knowledge of the provers knowing the existence of bug. Not only existence of the bug, but what the bug is. Okay, so this winning strategy is also very important for QBF evaluation. So in our work, we also propose a way to enable prove they know some certain winning strategy to make the formula evaluate to true or false. So that's another part of the high level idea is we can encode this winning strategy in automated reasoning. They call the hybridization or scalarization. We can encode them also using some formula and then reduce prove knowledge of winning strategy to proving the unsatisfiability of a certain formula. Okay, that is some other part I don't include in this talk, but I think it's also very interesting.
But when you do that process, can you extract?
I know that's the question you want to ask. So yes, so by theory, yes, if you have a Q resolution proof, you can always extract a winning strategy, and if you have winning strategy, you can also derive a resolution proof. But this is theoretical. It's like a theoretical work. It's like in polynomial time. But there is no like, for example, in like what the certain overhead is. And in our work, I may show later. So in our work, we show there exists some QBF formula. It can be verified in a very short time using winning strategy, but it takes a lot of time to verify its evaluation using Q resolution proof because the Q resolution proof is very long. It's very large, but the winning strategy is small. But this also happens vice versa. For example, we find some instances that has a small Q resolution proof, but the winning strategy is very large. So it's hard to say which one is better. It's case by case. Okay. Okay, now I want to show some additional evaluation of our work. So we benchmark our protocol on QBF eval. QBF eval is a standard benchmark for evaluating QBF solving, and we find that we can verify almost 70% of the instances within 100 seconds, as long as the solver can generate the Q resolution proof or winning strategy for them. And then we also try to see what affects the performance of our protocol. There are 3 factors. One is number of clauses in the proof and number of clauses in the proof and the formula. So together, the number of clauses. One is the proof width. Proof width is the maximum number of literal you can have in one clause. Okay, and one is the proof size, which is the product of the number of clauses and the number of widths. And as you can see, it's almost linear or almost proportional to the proof size, instead of just depending on the number of clauses or the proof width. Okay, and I don't know if it's good news or bad news, but I think it's a bad news. So it shows that given a formula, the proof size is you can optimize as the proof length, because this is proof length. You can either optimize the proof length or proof width, but their product almost keeps the same order. So you cannot optimize the proof size. Or there is no. This is like some theoretical results. Okay. And we also show some. Okay, I have some result here. So we also show like which one want to say which one is good, the winning strategy or the protocol using the Q resolution proof. And this is the result we have for winning strategy. If you think about the winning strategy, as I mentioned, you can first encode the winning strategy, which is the hybridization, and you need to check if the winning strategy is correctness. And the second step is reduce the problem to onset and checking the onset viability of the problem. And in our evaluation, we show that the bottleneck actually still lies in verifying the unsettlability of the formula instead of verifying the well-formedness of the winning strategy. Okay, that is the time decomposition of the verifying winning strategy in the KP. Okay, let me conclude my talk here. So in this work, we show a very practical ZKP for PSPACE, and we also find there are a lot of interesting problems if we have a full method and crypto people meet together. There are two very typical examples. One is previous work they are not proof for unsettlability, and this work they are not proof for PSPACE. Actually, all of them are fruit from both for method and crypto. Also something I want to emphasize here is when we do the evaluation, we find the running bottleneck actually comes from the QBF solver itself. So for many of the QBF instances, the solver failed to generate the proof. So instead of because our protocol is not being practical or efficient, it's the solver that cannot generate the proof we can consume. So that is where the bottleneck is, and very unfortunately, so in QBF computation, evaluation computation, there was a track called the certifying solver track. So in this track, all the solver are required to generate a proof. But this track was cancelled, I think 5 or 6 years ago because the participants was very few. So I use these slides to try to motivate people in automated reasoning to restart the track again. And there are a lot of future work we can do. For example, we can think about the application of this ZKP PSPACE and also make this proof system succinct or non-interactive. For now, we use VOLE based proof, VOLE ZKP backend. So that's why the now current ZKP protocol is interactive. Okay, that's all. Thank you.
When you're doing the order check for all of like the previous clauses to Y, can you parallelize when you're enumerating over all of those clauses?
Oh, you can. The short answer is you can. The better answer is we don't. We didn't do that. But it's in theory you can.
Yeah. First of all, thank you so much. It's really nice work, and I'm just trying to make some check work here. So can we, instead of using the polynomial as a root, can we use multilinear expansion?
You can, but if you use multilinear, I don't know if that will finally again reduce to sum check protocol.
But the degree of the polynomial now will be log the number of.
Even you use multilinear, then the degree can be also the degree. Okay. I want to emphasize that. One thing I want to emphasize, maybe I forgot to mention, the practicity of this protocol actually comes from the fact that the cost or the proof width in practice is relatively small. So the polynomial we have here, sometimes, with large chance, the polynomial is of very low degree. So most of the clauses contain just small number of literal. If you use multilinear, that means that the polynomial is like the degree of the polynomial. Even use multilinear is linear to the number of variable, right? Because you need to have at least have every variable's position in the polynomial.
So it is.
Because you need to hide which literal in the clause, so you at least need to pass the polynomial to the number of variable, right?
It's small. Then why does it
Yes,
doesn't make much difference?
Yes, because the degree is small.
Yeah.
Yeah, that's the things we find very useful, especially when we began this work. We try to find what kind of features in practice we can leverage, and this kind of feature is not like some theoretical guarantee, but that's what happens for real world QBF or real world Boolean formula, and that's also what happens when we try to design this algorithm, not only just about proving, but also solving formula. If you think about the QBF or set formula, it's as a PSPACE complete or NP complete, and it's always hard. But why we have a set solver that is so practical, that can solve so many formula like in seconds? That is because for most of the formula we handle in practice, they have very good structure, and we can leverage this kind of structure. And there, of course, exist some very hardcore instances, but to make the all protocol practical, that's something we can for a while ignore. Yeah.
Let's thank the speaker again.
Oh, by the way, we have a work code here. And if you are interested in playing with that, you can just go to or get this.